Welcome everybody to today's session on climate change. And I'm just going to introduce you to Ian Cable from the Collective for Climate Action and immediately hand over to him to start off.
Oh, thanks very much,
Over to
Jenny.
you, Ian.
Yeah, thanks very much, Jenny. Yeah, thanks for having me. I'm the education lead for the Collective for Climate Action, and I got a master's degree in climate change a long time ago, and I can still remember some of it, but I have to do a bit of revision for this. And I'm just going to kind of go through basically climate change. It's really expansive, so it's quite quick, and I'll be touching on lots of topics, but we'll just jump straight into it. So what we're going to do is go through what drives climate. Historic climate change, the cryosphere, tipping points, modelling, emissions, the biodiversity crisis, and also politics, because obviously all these things, they have an interplay in all of this to basically dictate what the situation is at the moment and what our likelihood of addressing it is and what we need to do. So to start off with, what drives climate is actually something called Milankovitch cycles. Like, we're in an ice age at the moment, and that just means that we've got permanent ice on the Earth's surface year round. And Milankovitch cycles basically describe the position that the Earth has when it's orbiting around the Sun. There's three parts to it. There's the eccentricity, which is like basically the oval shape of our orbit going around the Sun, so our distance from the Sun as we orbit it. There's precession, which is us, moving like a spinning top as we kind of spin in our axis as we go around the Sun. But the most important one is the axial tilt. And what this basically does is tilts us more towards the Sun and more and then away from it at different periods over a period of 41,000 years. And the importance of this is that the more we tilt towards the Sun, the more of the Sun's energy reaches the poles in the summer. So what that does is it stimulates melting of ice. Now, the poles will always be dark and cold in the winter and be more than capable of producing tons and tons of snow and ice. The important thing is how much of that ice survives through the summer. And what Milankovitch cycles do is they kick off warming and they start the melting of ice, which enhances the release of greenhouse gases. And the way that happens is it changes the albedo of the Earth's surface. So the ice melts on land and over sea, and then what you have is there's a difference in the reflectivity of the Earth's surface. So open ocean, when it's got no ice or anything on it, it soaks up 94% of the sun's energy. Bare ice on top of ocean soaks up 50, and ice with snow only soaks up 10, and bare land soaks up 80% of the sun's energy. So what happens is the sun melts back some of the ice. It reveals like dark open ocean, it reveals dark land, and both of those surfaces start to warm up. The land warms up and it melts permafrost, which is largely made up of organic matter that's been frozen in kind of suspended animation. And what happens with that is bacteria in the soil, they break down those substances or that organic matter to release CO2. And that's what's happening in the Arctic permafrost at the moment. And over the oceans, you've got places like the Laptev Sea, which is north of Russia. It's a very shallow sea and it's open ocean now. There's no ice on it for long periods in the summer. And it warms up the water so that the sediments at the bottom of that ocean, they warm up as well, and there's methane which is frozen in ice at the bottom of those areas of ocean. That melts, and a lot of the methane it bubbles up through the ocean and gets off into the atmosphere. So some of it gets eaten by bacteria in the water column, but the stuff that escapes has a really significant impact. And here we can see the effect of Milankovitch cycles kicking off these processes. So this is actually the thickness of ice here. It's really thick and it's really thin. They flipped it on its head so that it marries up with the temperature data. And you can see that pretty obviously, the higher the temperatures are, the thinner the ice gets. And we can see that that happens many, many times over time, going back over 450,000 years. So they don't map perfectly onto warm events, Milankovitch cycles. So here we've got watts per square meter. That's the amount of energy that the sun transmits onto the Earth's surface, depending on how close to 90 degrees the Earth's surface is facing the sun. So it's like at midday when the sun's at its hottest temperature, the sun's beating down on the Earth kind of in a straight line. So if we look here, we can see that there was quite a reasonably small Milankovitch event, but it created a lot of warming. And here we've got really quite powerful Milankovitch events with lots of energy from the sun hitting the Earth's surface, but it hasn't created as big a warming trend. And if we go back 22,000 years, then we go to the last glacial maximum. That's when there was most ice on the planet in the last ice age, we would call it, but that's actually called a glacial stage in a in an ice age, we have glacials and interglacials, and we're currently in an interglacial. So there's still permanent ice on the Earth, but there's less of it. And as you can see here, in this data, basically it shows that we should actually be peaking with our warming, and it should be starting to go down. We should be having reasonably rapid cooling, but we're not having that effect. And we know why. It's because we're emitting greenhouse gases and destroying the environment, which would soak them up. So there's an idea of climate denial, which is now thankfully becoming less of an issue. But what they used to do is they'd look at temperature data like this, and you can see that there's a clear pattern here going back from the 1970s. And what they would do is they'd take small sections of it and they'd publish that, and then they'd say, look, the temperature's going down, or the temperature's not going anywhere. But you can clearly see there's a trend of warming. And if you zoom out a bit more, so that was going back to 1970, the last one. If you go back to 1880, you can see that since the 1950s, it's been a really steady trend of warming. And what we know is that warming is happening now at least 10 times faster than at any time in the last 65 million years. And the other thing we know is that we're basically the only thing that is different to those other warming events. This is a really famous graph. This was from the third assessment report. And if you Google hockey stick, you will find that there's loads and loads of entries. Pretty much most of them will be all about how this is rubbish. The IPCC used this, and it's absolutely right. This is observational data in red, and the blue data is proxy data. And this is one of the things that they called out, or the climate skeptics called out, as being rubbish. And because what they did is they used things like tree ring data, pollen data, sea ice cores, sediment cores, delta 18 oxygen ratios in the ocean. And that was where all the blue data came from. And the red data is where we started recording temperatures, like in London, and also like pulling buckets of water out of the ocean in the Navy and sticking thermometers in it back in the good old days. So that data was really thin. And now we've got really good observational data everywhere, and you can see that over the last 1,000 years, basically, it's us doing the job. So one of the reasons climate is difficult to study is because there's a lot of natural variation in the system. So that creates noise. So this is the signal, a signal of pretty steady warming, and this is the raw data with lots of other natural variation making it look a bit messy. So there's something called ENSO, which is the El Nino basically, and that creates warming pulses every few years. So they strip that out, and you can see that it's you can still see that that's like a much straighter line. And also there's volcanic activity. This is Mount Pinatubo. In 1991 did this. And what it does is they release loads of gas, sulfate aerosols into the atmosphere, and also dust. And what happens is that shields us from the sun's radiation and creates cooling effects. So that's actually this bit here, not El Nino. So we can see that decline in temperature is much, much less here. And also we've got solar cycles which run over 11-year timescales. They peak in every 11 years. And so taking those three bits of natural variation out to confuse the data leaves us with a much clearer picture of what the warming trend actually is. Another problem with climate is that it doesn't change in a uniform way all over the Earth, because the Earth's a very diverse place. And so since 1979, we know that surface air temperatures over land have increased about twice the rate of temperatures over the oceans. And that's largely because of the cooling effect, or the moderating effect of water in the atmosphere. So, you know, if you're on the coast, you'll have it will never get really, really hot. And if you go to the rainforest where there's lots of humidity, it can't get any hotter than like mid to high 30s because there's too much water in the atmosphere. But if you go to places where they have a continental climate, like Verkhoyansk in Russia, there was an observation station there, and they recorded the highest Arctic summer temperature last year, and that was 38 degrees C. But because it's very, very far from the ocean, those kinds of areas like Siberian Arctic actually have really warm temperatures in the summer. They can often get up to high 20s and low 30s, but this is obviously a very, very high one. But it's just because there's no moisture in the air. So in the winters they get very, very cold, and in the summers they get very, very hot. And that's exactly the reason why we don't have hot summers, because we're an island and we're surrounded by very moist air and warm water. So looking at the cryosphere, this is the frozen part of the world. As I said before, we're in an ice age, so we've got frozen ice on land, or we've got ice on land all year round. And this ice is divided up into caps, sheets and shelves. And so ice caps are just the highest point on an ice flow. And flowing from that, you have the sheets that flow out in all directions often. And the only ice sheets we've got left really now are the Greenland and the Antarctic ice sheet. We also have shelves where those sheets meet the ocean, and this is the Thwaites Glacier shelf, ice shelf, or the ice shelf off Thwaites Glacier. And these are really important because firstly, you can see that this is really old ice because it's so thick. There's just no way. This is only going to be like a fraction of the actual ice in this area of sea here. But there's no way that that could have accumulated just through snow landing on ice in the sea. This ice is many, many thousands of years old, created on the land a long, long time ago. And as it flows out into the ocean, it kind of acts as a kind of plug, stopping the glaciers on land from being able to flow really quickly. And they also flow just out onto other areas of land. This is one of the dry valleys in Antarctica. It's not something that people really think about, but there are parts of Antarctica that have literally no snow on them at all because it's just too cold to make snow or for it to ever stay there for any period of time. So the ice shelves are really, really important, and we don't want them to break up, but they are breaking up, and that is going to be one of the things that enhances the flow of ice off land and into the sea. One important thing to remember about ice shelves, though, is their contribution to sea level rise has already been done because they're floating. So when they break off, they themselves don't really contribute to sea level rise, but as they leave the land and float away, they allow the land on the ice to flow into the sea more quickly. So we've got two parts to the cryosphere. We've got the Arctic and the Antarctic, and one of the most important things to remember is that they're basically kind of opposite systems to each other in many ways. So the Arctic is a sea surrounded by land, and the Antarctic is land surrounded by sea. So the Greenland ice sheet is melting in summers now, like the whole thing starts to melt now. And one of the reasons for that is just because it's surrounded by much warmer air. But so it gets into like plus temperatures now, positive temperatures now in the summers. But if you go to the Antarctic, for example, they've got really thick ice sheets on top of them, so many kilometers thick. And if you were going to the middle of the Antarctic in winter or in summer, you can still easily get temperatures that are, you know, -20, -30. But in the Greenland ice sheets, you can't get that anymore. The whole thing is kind of melting away, and as its elevation drops, as the ice sheet gets thinner, then that water, or the air, sorry, on top of the ice sheet will be able to be warmer because it's at lower altitudes. So we know when we go up a mountain, the air gets colder. So as these ice sheets drop, they will be exposed to warmer and warmer air, and the ice will melt more quickly. Greenland has tit, so it's going to melt. All of it is going to melt. So that will give us 20 meters of sea level rise, but over a period of about 1,000 years. So maybe less if our knowledge of ice sheets is well, not perfect, which it isn't. But that's the important thing, is that the ice on land is the stuff that when it flows into the sea, that's what creates sea level rise. So the ice that we've lost in the Arctic, that's not really a problem in terms of sea level rise. That's a problem for albedo that we talked about earlier. So as this ice disappears in the ocean, we're left with dark ocean that will absorb a lot more light than the ice would have done on the top of it. So at the moment, we've got about 25% of the ice melting is now driving sea level rise. When I was studying 10 years ago, the science was saying that it was all coming from thermal expansion still. So just the ocean slowly heating up and just getting bigger. So in the Arctic, it's mostly air temperature that's melting the ice. But in Antarctica, because a lot of it's so high, the air temperature isn't cold enough to melt ice in that way yet. But on the edges of Antarctica, what you've got is warm water warm water currents is actually the driving force. So that comes underneath these ice sheets. That's an ice sheet still, even though it's mostly submerged, it's still touching the ground. But they come underneath the ice shelves and they eat away at the bottom of the ice sheets. And what happens is, because this shelf is stuck to the edge of the ice sheet, it's still being forced into the water and it wants to float. So what happens is this thins away, it cracks off, carves off into big lumps and floats off into the sea. And as that cracks off more and more, you get bigger and bigger ice cliffs. And these are becoming something that we know to be more and more unstable, and they're much more likely to break up. So that's something that we've recently started to understand. We've recently understood this phenomenon as well, of the water melting away the ice underneath. And also it's about understanding what's underneath the different glaciers. If it's really, really rocky or mountainous under here, then the glaciers flow more slowly, and it's quite hard for us to get good data on exactly what's happening on the ground here. So where's the heat going? Most of the heat is going into the oceans, about 90% of it. And the way the ocean currents work, they move warm water from the surface of the ocean down to the bottom of it. And there are parts of the ocean still which they've not even noticed climate change yet, haven't changed temperature at all. So ocean circulations are helping to keep the Earth cool by constantly cycling the water, the warm water on the surface of the ocean down to the bottom. So they're kind of bailing us out quite a lot at the moment. That same cycle as well, it takes the surface water that has CO2 that's dissolved in it from the atmosphere, and it takes that down to the bottom of the ocean and takes it out of the equation too. So this will happen for many hundreds of years, because as we've created this thicker CO2 jacket around the Earth, that's going to be there. That's basically the rate determining step. So the energy that's getting trapped in the ocean, in the Earth system, that's what's going to be taken up by the oceans, and it's the life of CO2, or that CO2 jacket, which is going to be governing how long the oceans have to keep taking up heat and CO2 for. So, looking at the Arctic sea ice, there's some clear differences that are happening now. You can see that the volume itself has gone down by about 70% since 1979, and this is all ice here, disappearing at varying thicknesses. And you can see that since the mid-80s, and we've basically lost all of our multi-year ice, all of our 4-year ice, and most of it is just single-year ice. And that's important because it doesn't survive through summer melting. And so more and more of the Arctic Sea is exposed to the sun's radiation. And I used to really worry about that, but it turns out that even an ice-free Arctic, a dark blue ocean soaking up 90% of the sun's energy, will only contribute about 0.15 to 0.2 degrees C of an increase in warming. And that's set to be offset, hopefully, by China's commitments in 2060 and their kind of carbon reduction commitments alone. So it's still a problem, but from a warming perspective, but there are other impacts that it has, which actually we'll go on to in a second. So this is what's called deep water formation, and it happens from the circulation of the ocean currents around the Earth. And the Atlantic is really important in this, and that's why the Arctic ice is important, because the warmer the Arctic is, the less of this deep water forms. And the process is, warm water circulates up from the tropics. It comes past us to give us our warmish weather, and Norway and Iceland, and it comes up through the Arctic. And what happens is it releases its heat in the form of water vapour into the and just normal radiation into the atmosphere. But what happens is that water vapour becomes precipitation or snow, and so fresh water evaporates off the ocean, and it leaves a saltier water that then becomes colder. And that salty, colder water is denser because it's got salt in it, or more salt than the surrounding ocean, and it's denser because it's colder. So that falls down, and as it falls down in the water column, it pulls this current around. So this specific area here, because there's warm water becoming very cold water, is the most powerful part of the whole thermohaline circulation, what they call the global conveyor belt. And this basically distributes heat all around the Earth, cooling the tropics and warming the mid-latitudes like us. So it does happen a bit in the Antarctic as well, but because it's cooler water coming down through there, it doesn't have quite the same effect in terms of driving the circulation around. Now, this circulation does a series of really important things. It cools the tropics, it warms up us, so it makes both of those areas of the world much more habitable. It also it keeps the ocean mixing, so it makes sure that nutrients and warm and cold water all mix up in the ocean column. And that's really important because it helps keep the temperatures down globally, but it also helps get nutrients to the biodiversity that live in the oceans. And they're also really important at sequestering carbon dioxide out of the atmosphere. It also brings carbon dioxide rich water from the surface, where CO2 is dissolved from the atmosphere into the oceans. It takes that and takes it down to the bottom of the ocean too. So it helps sequester CO2, it helps keep the biodiversity in the oceans alive and keep it healthy, so it can also capture CO2 and sequester that and feed us with fish. And also, it also takes the CO2 out of the atmosphere and buries that low in the ocean column as well. And what's happening at the moment is it's slowing down, and we project that it will slow down for up to 45% by the end of the century. And what that means is all of those processes, the heat distribution, the nutrient cycle, the carbon dioxide being buried, all of those processes will be slowed down, and that has impacts for basically how much the natural system is going to help us out in terms of fighting climate. So one thing we try and do is we try and model all these processes to try and understand how they work, and also try and understand what's going to happen in future. We've got different types of climate models. The first ones were like global climate models, where they modelled like air, sea and land and how that interacted with each other. And then they built in the biological system to see how carbon moves through the system in Earth system models. So they're just like a beefed up version of a global climate model. And that basically makes us, shows us how we can understand how climate has changed in the past more clearly, because carbon dioxide is the driving force behind, or it's one of the biggest forces, along with Milankovitch cycles, behind what drives climate change. Then we've got something else called integrated assessment climate models, or integrated assessment models. These are the ones that the IPCC use. Now, all of these models take a really long time to run, like many months on supercomputers like the ones they've got in the Met Office in Exeter. But they're really, really complex. And the integrated assessment models, they also include the whole Earth system, but they try and include what humans are likely to do. Or what we will do. So they're the ones that create those emissions scenarios for how much carbon dioxide we can produce and how much of an effect it will have to give us 1.5 degrees or 2 degrees. But one of the other things they have in them that's really, really important and completely different to the other ones is they've got economics or economic models pasted into them as well. Now, economics, modern economics generally states that we can face economic growth in perpetuity. And there is a problem with that because it incorporates something called discount rates or social discounting into the modelling process. So a social discount rate is basically us saying the economy is going to grow, things are going to be cheaper to do because we're going to be better at doing them because we're going to be more technologically advanced. So basically it's going to be much easier for people in future to do any kind of carbon capture work, any kind of innovation, because it'll be cheaper for them, they'll be better at doing it, there'll be more money floating around, and there'll be more people to do it. So, but now we know that that's not true, and economists are talking about actually flipping those discount rates on their head to make it so that actually we're going to be less able to deal with these things in future. And I think the next IPCC models are going to have runs that incorporate that. So what that does is that's going to make it so that decision makers are made fully aware of the fact that we need to act now, because it's going to be easier to do it now than it will be in future, because we'll have more resources, more money, and we'll have a more stable environment. And we're not putting it on to the future generations who are likely to be poorer and more impacted by the impacts of climate change. So we're the real unknowns here. We know what climate has done over time. We've seen it happen, through our different proxy data that we've got. We know what happens when CO2 levels go up and when temperatures go up, but and when they go down. And we've seen how biodiversity moves around the world and how ecology changes as that happens. But we've not seen, the only thing we've really seen is, and we've got very scant data on it, is what we did at the end of the last ice age. And there was a lot less of us around, and we didn't live in a globally collected or connected, consumerist society that we live in now. So we don't know about what's going to happen with wars, famines, migration, and in terms of the global economic system, like how much money there's going to be floating around in future, because it's all based on trust. And if people think things are going to be worse in the future, they'll be less likely to lend money to people. So that kind of tightens everything up. But we need them to be as good as possible, because they do help us make decisions. So they're always wrong, but sometimes useful. I think Niels Bohr said that, I think. But basically, our emissions are going up, and they've continued to go up. COVID kind of put a little stopper on that, but this only goes up to 2019, but they have recovered since then. So they're still on the same trajectory as they were before. And that's to be expected, because we're just going to want to get our economies back on track. So we're putting it off again. We're kicking the can down the road for a bit longer. And if you look back at it, some people might say, well, Britain's only 1% of global emissions, so what's our problem? Why do we have to do anything? Well, actually, this is Europe excluding the EU, and we're part of this now. But if you look back, pretty much all of this up to the 1800s was us. We because of the Industrial Revolution, and us and Europe, wider Europe, we've clearly emitted almost all of, more than everyone else put together in terms of carbon emissions. So we've got a clear kind of moral incentive to do more than others. And actually, a lot of emissions targets have this baked into them, this kind of idea of grandfathering, how much we emitted in the past, informing how much we should cut now. And when you look at our emissions, you can see that they've been going down, which is great, and we've cut more than any other Western nation, which is also great. But if you look at our emissions reported by the government, often they'll give targets which are a bit more rosy than they actually really are. So here we've got like consumption-based emissions. That's the products that we consume that are made overseas, and when they're transported to us, and how they're disposed of overseas, and how we dispose of them. And those are much higher, 42% higher than actually our annual CO2 emissions. And the reason for that is because all of our heavy industry has been put in other countries. So they're doing the polluting for us. So we're letting them do our dirty work, basically. And we've cut coal, which is great. And that was quite a happy accident with Margaret Thatcher, who kind of got into a spat with the coal unions back in the 80s. And inadvertently, she was actually the first head of state to really look at climate change. But I think the Falklands got in the way of her actually doing anything about it. But much of our reductions come from actually offshoring our heavy industry and our polluting industries. So we've still got a lot of work to do. So what drives climate change now? Well, it's us. We're releasing greenhouse gases, anthropogenic ones, they call them. The natural systems do that as well, but they balance out when it's done naturally. So we're also destroying carbon sinks. So we're degrading the oceans and terrestrial habitats like forests. And these plant-rich ecosystems, they're the ones like peat bogs and forests and, well, many other terrestrial ecosystems as well. They're the ones that are naturally capturing and sequestering carbon. They're going to be really important in future because as we let them grow back and take over more of the land again, they will be able to have a positive effect on our trajectory of carbon emissions. But also we're getting rid of the animal species that help keep those ecosystems healthy. So like an established forest, for example, can capture and sequester something like 3 times as much CO2 as a forest that's just been newly replanted. So this takes us on to something called climate sensitivity. Now this is really important to understand because basically it informs our projections of climate. So a doubling of CO2 basically results in us having 2.6 to 3.9 degrees C of warming, which is really, really bad. 2 degrees was considered by the IPCC as, above that is catastrophic. And at the moment, if you look at what it was in the 1700s, there's about 280 parts per million. And just with CO2, it's just over 400, 415, something like that. But if you add in the other greenhouse gases like methane and nitrous oxide and fluorocarbons, then it takes us up to close to 500. And 560 will be double that. And if our climate settles at that level, then we will have warming of about 3 degrees C, which would be really, really bad news. But luckily, research coming out really recently has said that where we stop is where we stay. So it really adds weight to the idea of net zero, because once we get to net zero, then the environment will be able to work a bit more easily, just taking up carbon dioxide, because there'll be less of it going into the atmosphere, and it can start doing its job instead of growing trees and circulating the ocean to pull CO2-rich surface water down to the bottom of the oceans. So that's really, really positive. CO2 stays active in the climate through the carbon cycle. So it actually, we're just bulking this up. And as I say, we're destroying our natural ecosystems that help us to pull CO2 out of the atmosphere. But without fossil fuels, it remains constant. It keeps cycling between the ocean atmosphere and the biomass for up to 500 years. There is rock weathering that helps this out, and that's like a really permanent way to pull carbon dioxide out of the atmosphere. So there are certain types of rock which react with CO2 to form like solid products which won't allow CO2 back into the carbon system again. But we need to grow the biological components of this, so make healthier soils, healthier oceans, healthier forests and grasslands to try and make sure that more of this carbon going back down into the natural system stays there. And one thing that is a real problem is ocean acidification, and we've not really got a solution for that at the moment at scale, and it may be that we don't have one, and that's a problem because it impacts on the health of the oceans. So there are tiny photosynthetic organisms in the ocean which have exoskeletons like crabs do, but they're much smaller, and they can't make their skeletons if the ocean is acidic. So they don't grow to full size or they don't reach maturity at all, and that has an impact on the whole food web in the oceans. So there's geoengineering and natural solutions that we're kind of thinking about now. There's lots of natural solutions that we talk about, and they're going to take a lower cost to implement. But there's ideas like planting forests, seagrass meadows, which used to surround most of the UK, and we're working on building those back again. And peatlands, which we still use for compost even in the UK. Not destroying these ecosystems is really it's the first step that we should really be taking, because they're the ones that are most productive instead of the new ones that we would replant. And also kelp forests. These guys I was talking to a few months ago, and basically what they do is they're going to be growing more kelp and making that into something called biochar, which is basically charcoal, and you can do loads of stuff with that. But charcoal is a really stable form of carbon that won't break down or get back into the carbon cycle. So that's a whole other subject which I'm really interested in. But so they're doing that, and they reckon that they can pull a ton out with about £200 worth of investment. We've got artificial carbon capture, which is using machinery like this Climeworks and Carbfix, they basically filter like air directly through these systems, and they capture the CO2 and they either inject it into the geology, or they mix it with basaltic rock to make carbonate, and then it's kind of locked up like that rock weathering does earlier. They're really expensive at the moment though, and they will take lots of energy, and they'll take lots of infrastructure and machinery. So that's quite a resource intensive way of doing it. There's also geoengineering, and geoengineering basically is solar radiation management is the biggest one. Like volcanoes pump sulfate aerosols into the atmosphere, and also dust. They reflect the sun's rays back into the atmosphere or back into space, and they don't affect our warming. And if we are looking at that now, and it's using these sulfate aerosols can be injected at the right time in the right place around the planet, and we can actually reduce warming by 1+ degrees almost immediately. And just because of that, just because of the ease of use, the cheapness, and the immediacy of the effect, it seems very likely that at some point we're going to use that. But it'll be difficult to decide how to do that, because it will have impacts around the world in terms of rainfall, different weather events, and so that's a thing that international agreements can have to come together on. Another way is growing ice sheets. So as we know, the ice sheets are melting, but there are ways to people are talking about to kind of dam the ice sheets to prevent them from flowing out into the ocean, and other ways to pump water onto the ice sheets so that they can grow again or grow faster than they flow into the ocean. And these obviously will be incredibly expensive, and they're also being done in really remote parts of the world that are hard to work in. So the geoengineering side of things here, that's going to be really expensive, but that's probably one that we will see. So if you haven't got it already, it's really, really complex. It's all to do with our interaction between the environment, and it's informed by our politics, our societal values, how we use resources and the way we use them, or how much we use them, and also how we damage the environment or take care of the environment, because that's what's going to get us out of this mess. Largely it's going to be natural processes that are going to make a big bit of the difference. With that, where we stop is where we'll stay, research telling us. So when we get to net zero, it's going to be nature that starts to really do the heavy lifting. And also, but there's tipping points in the climate system. So steady states can be like the Amazon, moving from forest to savanna. And once they start to tip, then we start to see irreversible changes happening, like what's happening with the Greenland ice sheet, which has tipped and will melt away to nothing. There's also a lot of inertia in the climate system, so it's hard to turn it around once it starts. And we also refer to the biodiversity crisis because just of the amount of extinction that's happening. But it's important to remember as well, it's not just about global average temperature, which we talk about with regards to like 1.5 degrees or 2 degrees, because it has different effects around the world. And this is just as an example. El Nino is that climate phenomena which has different effects when it kicks off and warms the Pacific, making it drier in South America, South Africa, and wetter in sub-Saharan Africa, Arab states and North America, and even changes things in Europe. So it's really kind of unintuitive, but there's a bit like the butterfly effect. It has effects really far-reaching all around the world in different ways. We call it the climate and biodiversity crisis because we're going through a really massively increased extinction rate at the moment. The IBPES, which is another government body or a UN body which looks at biodiversity and ecosystem services, they did the biggest study of its kind, and they've basically come up with the conclusion that we are causing extinctions 10 to 100 times faster than ever in the past 10 million years. And it's mainly caused by land use. And in the ocean, it'll be to do with overfishing as well. It's basically like the marine equivalent of land use. And you can see, like, even in the UK, we're really good at maintaining a degraded state of our countryside. So a while ago, the Lake District applied to the World Heritage Fund or World Heritage Organization in the UN to say, we want to be designated as an area of outstanding natural beauty. And they said no, because you've basically got a massively degraded rural landscape, which is totally industrialized by sheep farming, and it's almost completely unnatural. So maybe you could have it as kind of an industrial or a kind of a cultural landscape, but it's just far too degraded for us to count it as a natural phenomenon. And when you look at areas like this in the UK, it does resemble what we've seen in the Amazon, for example, but we're just so used to seeing naked hillsides. But these are things that we need to sort out, because as I said, we need to have really strong, robust natural ecosystems, because they're going to have to weather the storm of a changing climate that's happening more rapidly than nature has ever seen in the past. So we're putting pressure on every part of the natural system to help us address the climate through deforestation, overfishing, agriculture, even renewables on land. That's a real problem in many ways because windmills and solar panels, they take up room and they disrupt nature, but they're still one of the best solutions we have. And also, what about concentrating on the right things? If you get a chance to watch Seaspiracy, I highly recommend it. It talks about data about plastics in the ocean and basically saying that, you know, the plastics that we produce, they are completely dwarfed by the plastic coming out of about 8 rivers in Asia, and also the plastic that comes, which makes up about half of all the plastic in the ocean, the plastic that comes from the fishing industry. So it's really important to try and focus our efforts on the things that are going to make the most difference. But the IBPES, they talked about 1 million species being threatened with extinction today. So it's happening at 10 to 100 times the background rate of extinction, which is a natural process. So tipping points, they all have feedbacks that are driven by greenhouse gas pollution. So we've got the albedo effect that happened in the Arctic, where more energy hits that part of the world. Darker oceans soak more of it up, darker land soaks more of it up. That heats up the air, melts the ice more quickly. Also ocean acidification, you know, greenhouse gases make the oceans more acidic, make them less likely to be able to soak up carbon dioxide through biological processes and also through its flowing around the earth as it stratifies, as it warms up, and also through environment management, so damaging the environment. One of the examples of the environmental damage one is in the Amazon, where obviously deforestation is happening. And if we do too much of that, then it could flip from being a rainforest environment to a savanna one, like we've seen in Africa on many documentaries. We've also got other ones like the boreal forests in Canada. So what happens there is rainfall is happening less, or it's decreasing. So the trees become more water stressed and they're more vulnerable to parasites or pest species like boring beetles. You have more dead trees. You have drier soil, drier trees, and it's more likely to get forest fires. And obviously those forest fires release more carbon dioxide into the atmosphere, and there you get more warming and then more drought conditions, and so the cycle continues. And Tim Lenton, who was at the university that I studied at, or who is a professor there, he studies these tipping points and published this paper, but he also studies other tipping points. There are tipping points that go back in the other direction. But one of the things that is known as well is the speed at which we approach these tipping points makes it more likely that we will go through them as well, or we can go through them earlier. So it's a bit like running at a door to kick it down rather than kind of pushing on it really hard. But there are tipping points in other directions, and people talk about how natural systems can have tipping points to go in the other direction, which we may want to exploit as we recover or sort out the climate mess. But there are also social ones. And we've clearly seen, I mean, I really looked at this really closely for many years now, and this is something that's definitely happening. Like David Beckham being lampooned by the Sun for flying too much, people are eating less meat, people are putting a high priority on climate in polls for political polling, and we've got cross-party support in many countries for net zero targets. I mean, it's a bit different in the States, but in the UK, there is no way that anyone is going to say that we don't need net zero. And you know, imagining that the Sun newspaper would have stuff like this going on a few years ago is just unthinkable. And also, we've got the most ambitious targets in the world now. They're legally binding, so we have to help the government get to them. But final thoughts, we're really late. We should have been doing this many decades ago, and it would have been much easier if we did. But we are where we are. We don't fully understand the climate and how the biosphere and climate will respond to what we keep doing to it, because we're stressing it in so many ways. And we don't know how human society will respond to the impacts of climate change. We plan to emit much more CO2 and then pull it out later with carbon capture technology on a massive scale. And that's a problem because we're going to be overshooting in terms of the amount of CO2 we want in the atmosphere. And we're technically capable of doing these things. We've got like proof of case efforts where we've done them, but we haven't got them on the scale that we need them. So it's a bit like saying, you know, we need to use a hammer to hammer a nail in, but actually we don't have the hammer. We just got the raw materials to make it, and we don't have anyone trained to use a hammer or knows what to not what to do with them. So we're still really unprepared, and there's a huge amount of work that needs to happen. We're still allowing for a 1 in 3 chance of going over 2 degrees C. So that's a huge risk. And this is quite old data now that's when that figure came out in 2013-14. But we're still really playing with a lot of risks here. And even meeting Paris gives us 3 degrees of warming with uninhabitable areas of the Earth where people are going to have to leave. So what we need, we don't have. We don't have the technology at scale. We don't have a clear plan of how to address this. We don't have full public buy-in. People are warming to the idea, but we still don't have enough. And also we don't have the regulatory structure like finance or industry. So neither of those areas are equipped to, or being forced in a way to actually address climate change. And also governments either have or they soon will run out of policies that people are happy to vote for that have like really high climate ambition. So that's the reason why we have to show governments, as included obviously, we have to show government that we support what they do, but we also support more ambition. And that's the key. And joining together and growing our voice is one of the most important things we can do that, because alone, we make a very small noise. But it's important that government just sees how many people are invested in this. So that's it from me. If you have any questions, I'd be glad to kind of grab them here. But also you can get in contact with me anytime. I'm also on Slack. Just have a look on our website on how to get on there. And yeah, I'll leave it there for the moment. Thanks very much.
Thanks, Ian. That was absolutely fascinating and really, really, it was so interesting. Any questions from anybody in the last sort of 2 minutes that we've got?
Yeah, sorry for overrunning.
I think we've got something in the sidebar there.
Oh, where was that? Oh, sorry. Here we go.
From Nan. Nan's asking, can we grow anything to assist?
Can we grow anything to assist? What do you mean, as in like personally growing vegetation?
Yeah.
Okay.
Or plants,
Oh yeah. Actually, well, if you go onto the CFCA website, you should see some resources on there about flowers that you can plant. That's one of the things that's actually really important for combating the biodiversity crisis, because insect species have fallen by about 70% since the 70s now. So it's really important that we do everything to make sure that we keep our own ecosystem healthy and all the biodiversity healthy in it. So yeah, if you go on our website, there's resources for that. You can get like seed packets from I can't remember who it is now, but I've got the links on there. But yeah, basically growing a healthy and diverse garden is really, really important. So anything that encourages wildlife to come into it, that's a really important thing to do. So yeah, we can do that personally. Or growing our own food as well.
Thanks.
I think Miles, were you going to come in?
Oh, hi. Yeah, that was really interesting, Ian. Thanks very much. I just read somewhere, and I don't know if this is true. You can put me straight on it. That in terms of CO2 sequestration, oak trees are one of the best. And I just wondered if we should stop buying from oak furniture land and buy from IKEA instead.
It's definitely best to source the most sustainable wood you can, and that's usually from forests that regrow as quickly as possible. So yeah, you are right to do that. It's definitely the best thing we can do, because obviously trees they have the biggest effect when they reach a level of maturity, and when we're replanting forests, they start to do most of their job when they're about 30 years old. And yeah, obviously oak trees grow a lot slower than pine does. So yeah, definitely a good idea to go for fast growing trees when we're sourcing our wood.
Okay, thanks, Ian.
Thanks, Miles. Natalia, did you want to come in?
Yes. Hi, Ian. Thank you very much for this. This was really insightful and somewhat scary, unfortunately. But my question is, what do you think is the one single action that as individuals we can take to make the most change? What do you think?
The biggest action you can take, without question, is voting on climate. It doesn't have to be a political issue, but just making sure that whoever it is, blue, yellow, green, red, just go for the most climate aware party and talk to people about it. That's the most important thing. People understanding how important the issue is to you, and also trying to make them understand as well. There are all sorts of personal choices you can make, and we've got loads of recommendations of that on our site as well. But the most important thing is making sure our decision makers see that we support much bolder action, and then they can put in place everything else that industry needs to do and that government needs to do to make sure that we are most likely to succeed in sequestering as much carbon as possible and cutting our emissions as quickly as possible. So yeah, vote on climate.
Anything else? Okay, we can do that. Is there anything else we can do?
In terms of personal actions, the biggest one is to fly less or stop flying. The most carbon intensive activity you can do is flying. Reducing the amount of meat that you eat is important, just because of not so much the impact of meat itself, but the impact of meat on the environment. So it prevents lots of areas of land and ocean from being able to be habited by just natural biodiversity. So doing that, but also there's some charities actually on our website that you can go to as well. There's a Vox article that's really good and getting other people to do the work for us. That's really important because, as I said before, those carbon capture companies, they're touting like $1,000 for 1 ton of carbon. But if you go to, there's a rainforest charity that if you donate $1, they can basically prevent the emission of 1 ton of carbon dioxide. And there's another one called the Clean Air Task Force in the United States who regulate the fossil fuel industry. So they're likely to do the same, or they do the same. And they've been externally kind of measured by, I can't remember what the Effective Altruism Movement, who look at the most effective charities. But those guys, and they're listed on our website, they're really, really useful. Like at Christmas, I got really boring and I just donated £25 each to the Clean Air Task Force, my family, because they don't need anything and they don't really want anything. So that was my kind of, selfish present to them. And then my brother did the same thing to me.
Oh, great. Okay.
But yeah, there's more actions on our website that you can look at too if you want to look in more detail. And Geeky Zero is a really great carbon reduction app that we're promoting. They've even got an active community that surrounds their work that you can engage with, like through Zoom meetings once every month. And they're really good. They've got different programs as well as the online app that you can use for yourself. But they've got ways for you to help engage your community and get people really moving on this. So that's a good one as well.
Amazing. Thank you.
Ian, thank you so much for that. That was absolutely brilliant, really insightful. And I'm sure if we had more time, we'd have loads more questions. Certainly I have. So this is going to be on YouTube, isn't it, Ian? If anybody wants to look at it or share it with their colleagues.
Yeah, it'll be on our YouTube channel. Yeah, I'll share the link. I'll share the link through this emailing list. But you'll be able to access it through Slack and our website as well. So we're trying to make it all neatly divided up into little playlists and stuff that you can see on our YouTube channel. So this one will be in there under what is it, climate change and where we are headings, I think. So that's all we'll put in.
Okay. I'm conscious we have overrun a bit now, so probably need to bring this to a close unless anybody's got any very, very quick last comments.
And one thing I'd say is just get in contact with me. And if you have any questions, I'm more than happy to answer them. I really love talking about this, as you can see. And we're going to try and have more kind of discussion type engagement in the CFCA, because that's something that our members have really called for. So, but yeah, just message me on Slack, or even just grab my email out of this emailing list, and I'll be more than happy to answer any questions you've got or recommend stuff to you if you want some of that too.
Okay, brilliant. Thank you so much, Ian. Really appreciate your time today, and thanks everybody for joining. It was absolutely superb. Thank you.
Yeah, thanks very much for having me.
Thanks, Ian.
Thanks. Bye.
Cheers.